Good afternoon, everyone. My name is Mr. Himanshu Nagpal, Assistant Professor in EC Department of AKGEC, Ghaziabad. Today we will discuss about the topic, one of the top photodetector, that is the Avalanche photodiode, and we will also discuss about the noise sources in the optical receiver. So first of all, we'll talk about the photodetector. What are the photodetector? Photodetector is a special essential component in the optical fiber communication, which detect the signal and convert the optical signal into the electrical signal. Okay, its function is to convert the received optical signal into electrical signal, and which is then amplified and filter out to get the original input signal. So following criteria which are essential for the photodetectors, or you can say minimum requirement which we should have for the photodetector. It should be of small size, suitable material, high sensitivity. The photodetector should be of high sensitivity is at operating wavelength. Means if a small amount of input comes at the optical receiver, it should give the output. That is, it should be very high sensitive and fast response time, or fast speed, and or you can say short response time to obtain the suitable bandwidth. Next point, it should have a sufficient bandwidth, which is essential to handle the high data rate. And the photodetector cost should be low cost with high reliability, and the minimum noise should be introduced by the photodetector so that SNR ratio will become higher. So we'll talk about one of the photodetector, that is the Avalanche photodiode. So this Avalanche photodiode uses the Avalanche process to get the additional performance. Clear? So photodetector is just almost similar to the PIN photodiode, but there is a process, that is a impact ionization, you can say Avalanche breakdown, which creates a difference between the APD and the PIN. The main difference of the Avalanche photodiode to other forms of photodiode is that it operates under a high reverse bias condition, and this enables the Avalanche multiplication of the holes and electrons created by the photon or light. Clear? So now see this one. As the photon enters if I say, let's say this one is one of the photodiode, that is the RAPD. This is known as the RAPD, that is known as the reach through photodiode. This is the RAPD structure. In this, you can say N plus P intrinsic layer, and this one is P plus, and this is given as the reverse bias condition. Means there should be negative. Clear? So this is connected to the reverse bias condition. The reverse bias voltage, when a low reverse bias voltage is applied, most of the potential drop is across the P N plus region. Most of the potentials drop across this region. This depletion layer widens with the increasing reverse bias voltage. Means if we are increasing the reverse bias voltage, the depletion region between this and this increases and reaches up to the intrinsic layer. That's why it is known as the reach through Avalanche photodiode. Reach through Avalanche photodiode. So after this depletion region widens with increasing reverse bias voltage until a certain voltage is reached, at which peak electric field at the Pn plus 1 region, that is needed to cause the avalanche breakdown. Clear? So now see this one. If I say as a photon enters the depletion region, as the photon enters this depletion region, it creates a whole electron pair. It creates a whole electron pair, and these carrier charges, or you can say this charge carrier, will be pulled up by the high electric field. As you know that when I'm providing the high reverse bias voltage, the electric field in this region gets higher, and when the photons enter in this region, when the photon enter into this region, the electron hole pair will generate, and this electron hole pair, this charge carrier, this electron hole pair gets pulled up by the high electric field, and this high electric field region photogenerated electrons and holes gain enough energy so that it ionizes the bounded electrons. Means when electron hole pair are generated, it have a very high energy, and when it gets a very high energy, it breaks down the another bounded electrons. Clear? These charge carrier have enough energy that they break down the further bounded electrons, and this process is known as the impact ionization. Clear? They gain enough energy so that it ionizes the bounded electrons, and this process is known as the impact ionization. So their velocity will increase to such an extent when they collide with the structure, they will create further whole electron pairs. Means that enough energy which is gained by the electron charge carriers due to the high electric field, they get enough energy that they will create a further whole electron pairs, and this carrier multiplication is known as the impact ionization. So the newly charged carriers are further accelerated by the high electric field guts, thus gaining enough energy, and this means you can say, if I say electron hole pair generated, and this electron hole pair further creates a electron hole pair, and this further creates a electron hole pair. If I say there will be a 1, 1, 2, it creates 2, 2 creates 4, 4 creates 18, 8, 8 creates 16. So this charge carrier multiplication is known as the impact ionization, and this gain enough energy to cause the further impact ionization. This phenomena is known as the avalanche breakdown, or you can say avalanche effect. This avalanche action enables the gain of the data to be increased many times, and this represents the 1 to 16 represents the avalanche breakdown, or you can say impact ionization, and this will decide the level of the sensitivity. Clear? So the minimum field required for the impact ionization, that is the threshold field, or you can say minimum voltage which is to be applied at the reverse at this junction. Clear? That is a threshold voltage. Clear? So multiplication for all carrier generated is given by the factor, that is m. Now you see, if I say if there is no avalanche breakdown, the primary current which is created, means electron hole pair generated, and this electron hole pair, this electron move towards where? This electron will move towards this in the upper side, in this side, and the holes will go to the upper side. So this primary current will create it, and that is known as the IP current. But when the avalanche breakdown is there, the current which is generated, that is known as the IM, that is multiplied photocurrent. This multiplied photocurrent is when occurs or exists when avalanche breakdown there. When avalanche breakdown is there. So the factor, by which factor the avalanche IM is greater than the IP, that is known as the IM. That is multiplied current M is equal to multiplied current divided by the primary photocurrent when there is no avalanche breakdown. So IM is the average multiplied output current and IP is the primary unmultiplied photocurrent. Clear? And this R represents the responsivity of APD is equal to the responsivity of the PN photodiode multiplied by the factor, that is M. This RPin can also be known as the responsivity or you can say unity gain. Clear? So the APD have some important features, that is it offers some advantage, that is due to the multiplied current, high level of sensitivity is there due to the avalanche gain. Means small amount of, if I say small amount of photons enters into this region or strike into this region, small amount of photon which is having a small energy, that small energy get multiplied by the due to the avalanche effect. So that's why the sensitivity get increases. And what are the disadvantage of APD is it requires a higher operating voltage, means high reverse bias voltage is required. Avalanche photodiode produces a much higher level of noise as compared to the PIN photodiode. Clear? So avalanche photodiode produces a very high level of noise as compared to PN junction photodiode, and this avalanche process means that the output is not linear. When M factor is when it creates 1 creates 2, 2 creates 3, 4, 4 creates 18, 8 creates 16, the factor is output will be non-linear. So now see, this one is the, so next we'll talk about the noise source and optical receiver. But first of all, before start with the optical noise at the optical receiver, we'll just see what is the equivalent circuit of the photodetector receiver. Clear? Now see, this one is the photodetector receiver. The first element of the receiver is the photodiode, and after this photodiode is connected to the amplifier, and between the amplifier and the photodiode there will be a load resistor. Clear? So the equivalent circuit of this photodetector receiver is equal to this one. This one is the photodiode. CD is the capacitance at the depletion region. RS, RL, this one is the RL. This RA and CA, this is the resistance and the capacitance of the amplifier. This one denotes the amplifier, and this shows to the APD. Clear? And R is the load resistor. So what are the noise sources in optical receiver? Or you can say this noise sources also creates a error in the optical receiver. So first of all, at the photodetector, first element is the photodetector. Photodetector can be of multiplied avalanche photodiode, or you can say it can be of unmultiplied. It is a PIN or PN junction photodiode. Clear? After this, there will be a load resistor, and then there is an amplifier. So at the photodetector, the noise which is present in the photodetector, it is the quantum noise, dark noise, background noise, or beat noise. Clear? If I say this photodetector is a avalanche photodiode or avalanche photodetector, then there is also will be a addition of some noise due to the excess due to the random gain mechanism. Now due to the load resistor, thermal noise will be there, and at the amplifier thermal noise will be there, and the noise due to the active elements, and there will be a surface leakage current in the circuitry of the amplifier. So the photodetector noise. So if I say the term that is SNR is very important in the communication. Okay? That is SNR is the signal to noise ratio. This signal to noise ratio should be very high in the optical, in the communication sector, and then at the receiver section of the circuit of the system. This SNR is equal to the ratio of the signal power. If I say this is a optical communication, so signal power from the photocurrent divided by the noise of the at the receiver, that is divided by the photodetector noise plus में amplifier noise power. Clear? So SNR is equal to the signal power from photocurrent divided by the photodetector noise plus में noise due to the amplifier, means amplifier noise. Clear? So these noise sources in the receiver arise from the photodetector noises resulting from the statistical nature of the photo to electron conversion, and also due to the thermal noise it is associated with the amplifier. So to achieve a high signal to noise ratio, if I want to achieve a high signal to noise ratio, the photodetector must have a high quantum efficiency to generate a high signal power, means numerator should be higher. When numerator should be high, means signal power should be high, and when the signal power is high, it means that there should be a high quantum efficiency of the photodetector. And the second point is the to increase the SNR, denominator should be minimum. Clear? And when I say denominator should be minimum, means the photodetector and the amplifier noise should be kept as low as possible. Okay? Now see, the sensitivity of the photodetector is also always determined by the multiplied photo current by the factor that is M. The sensitivity of the photodetector in optical communication can be described in terms of the minimum detectable optical power. So these are the sources of noise, and this one is the equivalent circuit. This is the simple model of the photodetector receiver, and this one is its equivalent circuit. So to calculate now my aim is to calculate the SNR, and this SNR is equal to signal power divided by the amplifier noise power plus में photodetector noise power, photodetector noise power. Clear? Now if I say, if a modulated signal of the optical power P of t falls on a photodetector, the power which is falls on the photodetector, that is P of t, the signal power, the primary photocurrent which is generated at the, if I say this is a PIN photodetector, then the primary photocurrent which is detected will be equal to what? I photocurrent is equal to quantum efficiency of your photodetector multiply में Q upon में H into में nu multiply में input power. Now, but if I say the photodetector is the avalanche photodiode, then there will be a factor of multiplication factor of the M. Clear? So to get the signal power, this photodetector should mean square value of signal current will be there. To get the signal power, that is I square S is represented by sigma square. This sigma represents the variance is equal to the I square into my P of T. Clear? The photodetector, for the photodetector, the I square S means signal power. You can say this is a signal power. You can say root means square value of the signal current. It should be equal to the primary photocurrent, clear, multiply में M square, and this M is the average of the avalanche, statistically varying avalanche gain. Because gain varies, that's why it is known as statistically varying avalanche, average of the statistically varying avalanche gain. So if I say the input signal for the sinusoidal input signal at the transmitted mode, if the modulation index is M, then input signal power will be equal to the M square upon my 2 into my I square P. Clear? Now see, this can be determined by this factor, that is M square by 2 into my IP, or you can say can also be, this signal power can also be written as I square PT into my M square. Now to calculate the SNRs, numerator we have determined. Now we'll talk about the denominator, and in the denominator the noise will be of due to the photodetector and the amplifier. So first of all we'll talk about the noise due to the photodetector. So principal noise which is due to the photodetector are the quantum noise, dark current noise generated in the bulk material of the photodiode, and the surface leakage current noise. Clear? Now see, first of all talk about the short noise or you can say quantum noise. This short noise arises from the statistical nature of the production and the collection of the photoelectrons when optical signal is incident on it. Means if I say at the photodetector, when the photon is incident on it, there will be a generation of photoelectrons. When this, you cannot say that every one photon generates a one pair of electron hole pair. It is a random process. It can be two photons can create a one pair of electron hole pair. Clear? Or you can say 10 photons hit this depletion, only 2 pair of electron hole pair generated. Or you can say 10 can be can generate a 20 electron hole pair. So this is it arises from the statistical nature of the production of electron and the production and the collection of photoelectron when optical signal is incident on it. This fluctuation determines the lower limit of the receiver sensitivity. This fluctuation means one may create one pair of electron hole pair, one may create 2 pair of electron hole pair, one may cannot create any electron hole pair. So this fluctuation determines the lower limit of the receiver sensitivity. So the short noise, due to this varying statistical nature of short noise, this I square short root mean square value of the short noise, that is current associated with the short noise, is equal to the 2 into my Q into my IP into my M square multiply my FM, and this FM is the noise figure associated with the random nature of the avalanche process. Now see, next noise due to the dark current noise, that is a photodiode dark current noise. It is the current that continues to flow through a bias circuit of the device when no light incident on it. Means if I say This one is the diode. This is a photodiode. When no photons enters on it, but still it creates a photoelectron current, photo current. That type of noise is known as the dark current noise. Means when no photons incident, but still there is a generation of photoelectrons, photocurrent. That is known as a dark current noise. And this dark current noise can be a combination of two. This is a combination of bulk and the surface current, and that is a dark current noise. This dark current noise arises from the electron hole pair that are thermally generated in the p-n junction of the photodiode. Clear? Now see, in APD, this liberated carriers also get accelerated by the high electric field, therefore multiplied by the avalanche gains. Means if I say initially photons enter on it and it creates a electron generation, electron hole pair. Clear? But suddenly the current gets stopped, photons get stopped at the or will not incident on the diode, but still the thermal process which has been started due to the avalanche gain, it will be continued and produces a small amount of current, that is known as dark current noise. And this dark current noise is equal to the 2 into my q into my id, where signal power due to dark current noise, that is I square dB is equal to the 2 into my q into my id into my f square multiply my noise figure multiply my bandwidth for post detector bandwidth. Clear? Now the next is the surface dark current noise. This surface dark current noise can also be known as the surface leakage current. This surface leakage current is occur generally dependent upon the surface defect, cleanliness of the bias voltage and the surface heat. That the current, the noise power related to this surface leakage current is equal to the sigma square ds into my q2 into my q into my il into my be. This il is the surface leakage current. So overall noise power due to the at the photodetector, overall photodetector noise current will be equal to the signal noise due to short noise, due to dark current noise, and due to the surface dark current, surface leakage current. And combination of all these, you will get the 2 into my q into my id plus ip into my m square fme into my be plus my 2 into my q into my il into my be. Here be also will be there. So now amplified noise has been considered. Now we will consider the amplified noise. So at the amplified noise, that noise is due to the resistor present at the receiver. This the thermal noise which is created due to, at the amplifier, and that is given by the thermal noise power that is at the amplifier, that is known as the I square t is equal to the 4 into my k into my bt divided by RL into my be. Clear? This is equal to the 4 into my k is the kb is the Boltzmann constant, is the temperature, b is the post detection bandwidth, clear, divided by the load resistor, and which is generally which have a very high value. So thermal noise, if I say RL have a very important role in playing in having a noise due to the amplifier. So overall signal to noise ratio will be equal to signal power upon photocurrent divided by the photodetector noise plus my amplifier noise. All the values of the signal power in the photodetector which has been detected, that is signal power value is this one, or you can say this one. Overall noise will be this one, thermal noise. So put all these values, will get the signal to noise ratio power will be equal to this one. So if I say, I am saying that RL have a very important role. So what should be the M value? Because M is coming in the numerator factor and also coming in the denominator factor. So if I say m can be, if I say put the value of m very large, but therefore signal noise, photo detector noise can also be greater. So m should be optimized to get the optimized signal SNR, or you can say maximum SNR. So to get the maximum SNR, this m factor should be optimized. So when m factor should be optimized means to get the we have studied the maximum and minima theorem. To get the maximum value, denominator will discuss differentiate this equation with respect to m to get the optimized value, and optimized value of m coming out to be 2 into my q into my il plus my 4 kbt divided by rl upon my x into my q into my ip plus my id. So this we have discussed about the APD, working of the APD, and we have discussed about the photo sources of noise in the photo detector, in the receiver, optical receiver, and we have also calculated the signal to noise ratio at the optical receiver when the photo detector is the APD. So the book which I have referred preparing this slide is the Optical Communications by the Gerd Kiesel and Optical Communication by the John M. Senior. Thank you.